So begin with a very blank version of the beautiful images we've seen in the conference. We start with an inflationary era and then inflation ends. This is the spatial slice on which we are computing correlations of fluctuations. Then we have CMB and so on. The reason why we are interested in computing these correlations are because these are the observable output of inflation, which we can map to current day cosmological observations such as the CMB and probe the inflationary era. Consider a scenario of a minimally coupled massless scalar field which is undergoing slow roll in its potential. The slow roll is what gives us the inflationary background, and at the gauge where the inflaton fluctuation has been set to 0, the curvature perturbation arises as the scalar degree of freedom in the spatial part of the metric. Now this 2-point zeta function can be mapped to and hence has been observed from, the amplitude of it has been measured from the CMB temperature fluctuation, the 2-point temperature fluctuation. And also there are bounds on the non-Gaussianity parameter corresponding to various configurations of the 3 modes. To be more precise, the object we are interested in computing is the inner correlation, where we are computing the expectation value of some operator O on some state psi at t time tau goes to 0, which is the end of inflation. But the state psi has evolved from some background omega at early times. As the field evolves, there can be interactions in the bulk which will reflect in the boundary correlations that we are computing. These interactions can be contact, exchange, or loops. Now the reason why such loop corrections have not been studied and computed in the literature for a very long time is because they are expected to be very small. So if you look at this one over here, which is the one loop correction to the path spectrum, which is the same diagram, it is at least 10 orders of magnitude success with respect to the true level result. So practically no group of ever observing. Weinberg was the first to stress that even if these predictions are unobservable, one should still compute them to explore the field. With this motivation, he computes this diagram in the presence of n natural spectators in this plot, and the structure of the loop correction he got was this. S is Hubble, K is the mode, C is some spin-dependent constant, and he had this log of K by mu. It was later pointed by Senatore and Zalvariana that there has to be a mistake in this computation, which is signaled by this logarithmic structure. Notice the argument is a co-moving scale by physics. Now, as you would do even in flat space loop computations, you have to choose a suitable renormalization scale to avoid the problem of large logarithms. To do that, one would compare the numerator with the denominator. And in this case, to do that, you have to convert the co-moving scale to a physical scale. But here you would do this at the cost of introducing the scale factor, which means the 2-point function now depends on the scale factor. But the scale factor by definition is unobservable, just corresponds to rescaling of coordinates. So there has to be a mistake in this computation. The point is that implementation of dimensional regularization in this setup is facile because, unlike in flat space, there is non-trivial dimensional dependence of the nodes in this setup. So if you compute this diagram with 3-dimensional nodes, you would end up with this antiphysical logarithm, like Weinberg did. But if you account for these order delta contributions, you would actually cancel this antiphysical node, and you would get log of h by mu. Notice that this is a ratio to physical scales, and this makes sense. Motivated by this, we ask the question of what would happen for higher point functions. In particular, since in the past spectrum case, spatial transmission invariance influences both legs to have the same momentum, but that's not true for bispecific. So you can have a linear structure. You can have logarithms that depend on the momentum. Also, whether such antiphysical logarithms arise for loop corrections for higher point functions, and whether accounting for this order delta contribution would lead to the cancellation. What we see is using d-dimensional group is not enough for higher point functions at one loop. As you can see from the result of this computation, which is shown over here. This diagram has been computed with pi dot cube and pi dot cube interactions, which are exactly interactions we took from the electric conclusion. In this answer, you will see a 1 by delta term of Cosmological regularization. You see logarithm of ratios of physical scales, of co-moving scales, and you see a log k. Now, with appropriate factors of mu, this will have turned into a log k2 by mu, which is precisely the antiphysical logarithm that emerged in Weinberg's answer that was corrected in Senatore's computation contact counter term is proportional to this term. Notice that the relative factor between 1 by delta and 1 by delta that comes from the counter is the exact same factor of minus half that also comes in the bispectrum answer. And so without explicitly renormalizing the theory, this shows, oh no, 5 minutes, okay. This shows that since the counter term will cancel the divergence in the bispectrum, it will have to take away the unphysical logarithm. So the lesson we learned is that loop effects are small, unobservable, sure, but they're important. And they're recently being studied. There's a growing interest in the community to study them in the context of testing how robust tree-level predictions are for higher stability in the context of PBS formation. But the next work that I'm going to very briefly mention, because I don't have time, is, as my professor advertised yesterday, regarding importing aspiration of the S matrix community into cosmology, which is to understand how do physical properties such as physical principles such as unitarity and causality would manifest themselves in the analytic properties of scattering of physical observables. In flat space, the key ingredient to doing this was a knowledge of the analytic properties of scattering amplitudes in the complex plane of kinematics. But in cosmology, this is missing. And beyond tree level, there is no systematic understanding of what is the singularity structure of correlators. And the very simple reason for that is these integrals are extremely difficult to compute. And just to give you a flavor of this is the answer you would get corresponding to this diagram with just a different interaction taken from the EFT of inflation. This is definitely not pleasant on the eyes, but if you look past the ugliness, you would start to see the glimpses of the story I just told you. That for each piece that you see over here, you have 1 by delta term and an unphysical log, but the relative factor once again is minus half. And so these unphysical logs are once again cured once you renormalize. Anyway, thanks to people like Bauman, Pimentel, Nima and others, we know what is the singularity structure at tree level, but we do not know what happens at loop. So what we did was, we inspected the integral structure of correlators that allowed us to formulate diagrammatic rules that you can use to list out the singularities that an endpoint function at one loop will have without having to perform any computations. All you have to do is identify certain subgraphs and the external energy injection into these subgraphs. I would have liked to demonstrate the rules, but I really do not have time. So the moral of the story is that the one thing that I would like to mention is the rules tell you that the logarithms that are produced, the branch curves that are produced from these loop diagrams are all sums of energies, the energies that flow in the loop legs or the external legs. So this immediately tells you that if you look at the analytic structure of these correlations in the complex plane of kinematics, you would find poles and branch cuts in the negative real axis. For example, if you look at this diagram over here, this would in the complex plane of omega 1 plus omega 2, where omega 1 and omega 2 are the energies of these two legs, has 3 poles and 2 branch cuts, and in the complex plane of omega 3, which is the energy that flows in this leg, it has 5 poles and 3 branch cuts. So, and so that you believe me, here is the explicit computation of this diagram, which is a 3-point function at one loop with a phi dot cube interaction for the cubic vertex here, and sigma being the conformally coupled scalar running in the loop. Using the rules, you would predict log at SL plus S, where the small s is the magnitude of the momentum exchange between the loop sites, tau 2 and tau 3. A logarithm at SR plus S and a log at SL1 plus S. That's precisely what you find if you compute this diagram. Once again, you don't have any unphysical logarithms hanging around in the answer. This is the renormalized correlator. You have dilatation invariant logarithms, and you find a log omega t. Now, if I had the opportunity of telling you the rules, you would have seen that you don't actually get a log omega t from the roots. And interestingly, we find log omega t in all of our inflationary correlations. This is a feature of de Sitter. And it's interesting to mention because there's a theorem that goes by the name of cosmological K-Lin theorem that was proposed in this work that says that there cannot be a total energy branch point for a cosmological K-Lin correlation. Now the point these people missed is that this is only true in flat space. Because in de Sitter, you would actually produce a log omega t not from loop integrals but from time integrals. And finally, all of the logs that these rules would predict would never lead to any unphysical logarithm. In a renormalized correlator, they'll always repackage themselves to form logs of ratios of co-moving scales. Right, so the conclusion is trust renormalized answers, otherwise you end up with unphysical logarithms. And now you have new diagrammatic rules. You don't have to perform very lengthy, complicated integrals. You can immediately predict the logarithms that are going to be produced in a diagram, along with the log omega t, which is a feature of de Sitter. The next few steps would be to see how these rules generalize beyond one loop and two sides. What would happen if you consider fields of different spins or masses, because these were all massless scalars. What would happen if you start to try to compute these correlations using interactions from the, let's say, third order or fourth order of curvature perturbations, because that would include complicated interactions. Finally, the hope would be to get some sort of UV-IR dispersion relations and see whether we can say something about get some sort of positivity bounds for the EFT coefficients for an inflationary EFT. Thank you.
Thank you, Shukrita. Are there any questions?
I'm just curious, what is the amplitude of the one loop correction to the ratio of the one loop correction to the zeroth order bispectrum?
One loop correction to the tree level.
Order. Tree level 3-point function. Do you know this amplitude? I'd like to know how large are the loop corrections?
Right, so they would be suppressed by factors of Hubble by M Planck. If I'm not wrong, this would be somewhere around of
they will be of the same order.
What do you mean by same order?
I mean, in terms of H by M Planck, I would expect them to be of the same order, and they will be suppressed by coupling parameters, I would imagine.
No, because you have for the 3-point function at contact, as opposed to for loop corrections, you would have more number of legs as well as vertices.
Okay.
Now, as you introduce more legs and vertices, you would get suppressions of Hubble by M Planck.
Okay, so maybe there are H by M Planck.
Yes.
Do you know how much?
Plus there will be slow roll suppressions.
Do you know their values? I
Possibly.
presume you are calculating, these are meant to be in slow roll.
Yes.
So do you know how much suppressed is it?
Possibly a factor of Hubble by M Planck cube, but I'll get back to you with the exact factor. But I can tell you that these will be suppressed with by these factors of Hubble by M Planck.
Okay. Yeah. Have you looked at what happens when there are departures from slow roll?
No. This is strictly in the slow roll scenario.
Okay,
yeah.
Thank you.